Okay, assalamu alaikum wa rahmatullah. Good afternoon, everyone. Today's class actually is all about the assignment that we had last 2 weeks. So we will go through, we will answer the things together. We will try to measure the speed up, the overhead, and everything. Okay, exactly as I requested from you in assignment 1 and assignment 2. Since we already have finished our synopsis, so everything inshallah will be like making more recap to review together, to take some practical examples to solve some scenarios together. Okay. So in here, in this assignment 1, we given a sequential program that finds the prime numbers, even numbers, and odd numbers in the integer domain from 1 to n, where n is set to 100 in the program. So I shared with you already the source code, exactly this one I shared with you last time. So when you run the program, you will get this result. But the program here, if we go through, you will see that the program is only one class file, which is the program.cs. Then after that, inside the program class, we have, this is the class actually, and we have one main function, which is the start point of the program. So in here, in this main function, the program will start sequentially as normal. Even if the program is later changed to parallel or multitasks program, then the start point is always will remain as sequential startup. So the call of the functions will be sequentially done. Okay, so here, as normal as any program, we started by initializing the values. So we initialize the n by 100. Then we take or read the start time from the system using this data type. Date time class and the property now. So the property now will retrieve date and time together. But we are actually concerning about the time only. But because sometimes you start your experiment or you run the program at the first, for example, at the time of 23 and for example 58 minutes. So after 2 minutes, it will go to the other day, right? So that's why we need to calculate or we need to record the date and time together. And after that, we have to minus them from each other to get exactly how many hours or how many minutes, even if the day is changed. Okay, so this function here or this line here is only to tell the user to wait until the result is being ready. Okay, then after that we call 3 functions in a row. So we call the prime up to n and events up to n, odds up to n. So those functions actually, if you right click here and you go to definition, you will directly go to the function, which is also in the same place here. If we collapse this, as you can see here, we have this function, and this function. So we have odds up to, evens up to, primes up to x. Okay, and this is the main function. So the program will start from here. Then from here we will call the 3 functions. Then after the 3 functions finish their processing, then after that they will save their results here in those variables. Okay, so here we have one variable for the primes and one variable for the odds, one other variable for the evens. Okay. Also, we have these 3 Boolean variables. So those Boolean variables, we initialize them with the value of false, because this these are only flags to be used later when the functions, these three functions finish their tasks. They should change this value to true. Okay, to tell the main program, because these functions later will be running in different threads. So different threads cannot communicate directly. So they have to use the shared memory. So this is going to be a shared memory actually. These variables are defined in the shared memory. So that's why they are accessible from any thread. And here, for example, if you see in the first function of the primes, when they find all primes and they finish, then they have to put the result. They have to put the value in the result until they finish. Then after that, no, sorry. They temporarily have to save the result here in this variable, local variable. Then after they finish all numbers, after that they pass it to the public or the shared memory variable. This one, primes, which is this one. Okay, so the result will be saved in that shared variable, and after that this flag supposed to be changed to true instead of false, which means that the function already done its work. Is that clear, guys? Is that clear? Anyone here?
Yes, doctor.
Okay.
Sí, doctor.
Okay, good. So before I forget, please find the videos on the YouTube channel, my YouTube channel. So especially for your final exam, if you want to review anything or to check my courses or my classes, it would be much easier for you guys if you have any confusion or any other things. Also, at the same time, you can contact me if there is any unclear things. Okay. So here, after the function finish, the result will be saved in the shared memory here, in the shared memory variable. Okay, depends on the function. Then after that, the relative flag for that function will be changed from false to true to tell the main function that that sub function is already done its work. Okay, so from this point, for the sequential programs, actually, the second function will not be called until the first function finish. So this function, actually, the cursor will go from here, directly jump to that function here, and go line by line until it finished. Then after that, go back to this point to call the other function. Then from here, it will go directly to the second function. It will go line by line until it finished. Then it go back here to call the third function. Then from here, it will go back here to the other function. It will execute it line by line until it finish. Then after that, it will go directly to the main function again, and it will start running this line after another. Okay, so sequentially, you cannot see the waiting message until the three functions finish, right? So this function will not work ever. So even one time it will not work. Why? Because when the cursor come to here, these three variables are already true, right? Because the three functions have already finished their tasks, so they change these three flags to true, right? So the while function, the while loop here will not work at all during the sequential code. Okay, but I put this to help you guys. I just put this to prepare the program for the parallelization. Okay, so for the sequential, when the cursor come here, the condition, this condition will be false. Why? Because this one is false. Evens found is true. So the result here we check whether it's false or not. So it's not false. It's not false here. It's not false here. So this condition finally will retrieve the value of false to the while loop. So the while loop will not run even one time. It will not run at all. It directly will go to the console clear to clear the screen. Then after that, it should take also the current time after it finishes. It will read the time again, then it will minus the start time that we recorded here at the beginning. So the difference between the current time and the start time that we recorded before will be saved here in the duration variable to be printed later on the screen. Okay, so after this, it will go and print this dashes. Then after that, it will print the series of primes. And after that, it will print another dashes line. Then it will print the series of even numbers. After that, dashed line, print the series of odd numbers. Dashed line, print the processing time is equal to the time that we already used or consumed to calculate or to finish the task of finding the three types of numbers based on the three functions. And after that, it will print the dashed line. Is that clear, guys, until now? Is that clear? Any question before I move?
Clear.
Clear, doctor.
Yeah, it's very C# is very similar to Java, much cleaner than Java, but the syntax is also more clear here in C#. But the concept, the main concept, is very similar to Java. So that's why I think you already have taken the Java course, right? Am I right?
Yes, doctor.
Anyone doesn't take Java course before? I don't think. Okay. So this is how sequentially it will run. So let us run now the the program and see how it works. Okay, this is the console screen. You see here, it doesn't print anything. It only prints this. Then now the functions are called one after another. And because the functions does not print anything on the screen, that's why you cannot see anything, because the printing is supposed to be inside the while loop here. And because the while loop is not yet reached, the cursor is not here. The cursor is still moving from the primes function to the even function, and after that to the odd functions. And once the three functions finish, then the result will be printed directly after that, without going through the while loop and waiting for threads to finish, because here we have only one thread, right? So as you can see here, the execution time, I'm going to record that numbers. So the TS time for sequential equals to 25.212. We will take only the first three numbers of the fraction. Okay, so I will repeat this multiple times. I will repeat this 3 times only to tell you how to make this. If for example in the real life you wanted really to calculate that, to calculate the speed up based on a real application or whatever. Guys, this skills actually is very rare, even with very high skilled programmers. Many of the programmers, the high skilled programmers, doesn't know how to write multi-threads programming or multi-threads programs. Most of the programmers doesn't know how to write that, doesn't know the concept, doesn't know, even if they know the concept, doesn't know how to deal with that, doesn't know how to handle the threads, how to manage them, how to kill the threads, how to call back from one thread to another. That's why if you learn this will give you a very good tool in your hand. Very good tool in your hand. This is actually a practical tool which is highly requested. highly requested. And even if you search about jobs in, for example, in the LinkedIn or Indeed or Job Street or whatever, it's very rare to find companies that looks for people who know how to build multi-trading programs. Why? Because mostly the companies that need multi-trading programs, they train their own staff. Actually, they take normal programmers who doesn't have any idea about multi-trading, then they give them special courses to understand how to deal with this and that and so on. Then after that, they keep them in the company. They try to keep them, and their salary will be high. Okay, but if you have the background from the beginning and you go to work in a company that even doesn't require you to have this kind of skills, but after you start working, you show them that you have this skill, believe me, your position will be improved. You will take a step forward compared to the other people who don't have this kind of skill. Okay, so this time you see, this time we have better running time, 605. Let us try another time. Okay, I just want to tell you something, guys. Don't expect that this program, when we convert it to multi-trades, don't expect that this program necessarily to improve the time. Why? Because this problem that we work on now actually is very small. That's why sometimes when you convert a program that's very small to multi-trading, then sometimes you face the opposite thing that you expect. So you expect that the time will be improved, but suddenly you find that the time is more worse. Why? Because your problem is more smaller than the complexity of multi-trade. Okay, that's why you have to balance, you have to understand your problem, you have to understand the nature of that problem and so on. Before you think to change things to parallel. Okay, now here we want to calculate the average. So what we need to do, we open the calculator, we count to 5.212 plus 22.605 plus 23.444 equals 71 divided by 3, because we have run the thing 3 times. So the average is 23.753. Okay, so this is the average for the AVG TS. Okay, let us put another dashed line to start another step. Okay, now we are done with the sequential. Let us now move to return things back to parallel. Here we already disabled these 3 functions, these 3 calls for the functions that we are targeting. Let us start now that functions in different threads. Okay, so here what we need to do is to create a new thread called primes up to, or whatever the name, you can decide what name you want to use. Then after that you initialize that thread, so new thread. Then after that you open the braces and you use the lambda expression. Why we use this? Because our function is parameterized, so we have to pass the n value to the function, right? So if we don't have the parameter, we just need to call it like that. If the function doesn't have the parameter, this parameter, you see, now I am going to remove this. I'm going to remove this. You see now the call. The call is not okay. Why? Because we still have we still have to mention the function. So here primes directly, primes up to, like that and like this. So this is how we call the function. This one is cannot convert void to a system parameterized. This one doesn't need this. Yeah, just we give the name of the function. Okay, we give the name of the function. Why? Because the function doesn't have parameters. But in our case, because the function has parameter, here we have x, which is a long integer that should be passed from the main function. So here the call in C# requires us to initialize the thread using the lambda expression, where we have to open and close braces. Then after that we use equal, greater than, then we put the name of the function, we open braces, and we list the variable, the parameters. So if let's say we have more parameters, so for example we have n, x, y, and so on, we list them exactly as they are defined in the function interface. Okay, so this is only to initialize the thread and to tell the thread what kind of function it have to run and what kind of parameters we want to pass to that function. Then after that, later we start the function in a different thread. We start the thread that runs the function we mentioned here. Okay, so this is this, if you recognize, this one is a small p, right, which is the name of the thread, but the name of the function is capital here. That's why this is the name of the function, and this is the name of this thread. You see, even when I select this, highlight this, this one will be highlighted. But if I highlight this, this is different than that, because C#, Java, C++ are all case sensitive. So capital, you see, when we select that, it highlights the function. Okay. So after we start the primes up to in different in different thread, we go to initialize another thread with and link another function to that thread, which is events up to n, and we call it. We call that second function in different thread. Then after that, we initialize another thread for the other for the third function. Then we start the third function in different thread. Okay, this can be done like that, and also can be done this way. We can initialize first the functions, then after that we call them directly. Okay, so now if you can see in the sequential, when the program was sequential, the call of the functions is sequential, right? One after another, and the second function cannot be called until the first function finish, right? So that's why we cannot see the hashes printed on the screen. Why? Because when the cursor come to here, all these variables are true, 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 because the three functions already finished their tasks. That's why we couldn't see the hashes printed on the screen. But in this case of multiple threads, we defined three threads here, one for each function, one thread for each function. Then we started the threads directly, so the execution will go through the main function here. We'll start with initializing the n value with 100, the n variable with the value of 100. Then after that, it will record the start time. After that, it will print please wait. Then we will initialize the three threads. We start this thread, this function in different thread, and we immediately call the other thread, second thread, and we move forward. So those threads are still working in different threads while this program is on progress. So this program actually will call that threads and move forward until it come here. So the first function actually doesn't finish yet. So the primes found is false. So false equal false means true. Then this one also true, this one also true. Then it will go inside the while, and the loops here will be executed to print hashes on the screen. So that's why now if I run, you will see hashes printed on the screen. Then once the functions, the first function, for example, finish, so this one will become true equals to false, it will become false, but we still have OR here. We still have the other function doesn't finish. So that's why this false equals to false will give true. So even one function doesn't finish, the program still need to wait for the three function until they finish. So once the three functions finish their tasks, then the while will stop and will clear the screen and start, will take the duration time. Then after that, we'll start printing the results on the screen. Okay, let us run now and see how it works. Okay, now as you can see here, this is the console screen. Okay, you see the hashes now printed? Hashes now printed because now we have 4 threads are working under this program. 4 threads. Okay, so if we want to see what happened, we can open the task manager. We can open the task manager here, and we can find what's the, okay, it's already finished, that's why we cannot see it here. Okay, now the result is already displayed on the screen. So let us see here, time is 25, right? So now the time is already more than the sequential. Why? Because here the problem is very small. The problem is very small to be solved, and we add the complexity of multi-threading. So because of the complexity of multi-threading, a lot of overhead will be added to the execution time. Then the total time of the program will be sometimes more than the sequential time. That's why you cannot see the improvement here. Okay, let us now record that time. So we need to record TP equals 25.128. So this is the first time. Let us close this, run again. So here we have multiple threads. You see, until it finish. Then after that, we can see the result. If you can find the program quickly before it finish, I don't know, it finished. Yeah, after I found it, it finished. Okay, now the time is 23. TP equals 23.474. Then another run. TP equals, let us finish, start again. I couldn't catch up with it. Okay, so now time is still 23.887. So if we calculate the average, as here, but this is the average TP. So normally I expect that the time is going to be larger than the time we used to get in sequential. So here 25.128 plus 23 plus 474. I don't know what happened. 474 plus 23.887 equals 72. You see, last time we got 71 divided by 3. So here the average is 24. 24.163. You see, now there is no speed up. There is slowdown here. And instead of getting speed up, we got slowdown. Why? Because the problem is very small. The problem that we try to fix or to solve in parallel, it's very small. If this is the size of the problem, my advice, if this is a real case actually, so my advice is to keep it sequential. You don't try to make it parallel. Why? Because as I said, the parallel has its own complexity. So the execution time will be equals to processing time plus parallelization overhead. So it will cause sometimes a more execution time than the time required for sequential program to be finished. Okay, as we can see here. Fortunately, we could get this result because in most cases, if the problem is more bigger than this, we cannot see that slowdown. We cannot see that real scenario of slowdown. Okay, so let us now try to make the problem a little bit bigger. We try to make the problem a little bit bigger. Okay, so let us consider, for example, 200. The n we make it 200. So instead of this kc, this one control ku. So we return it back to sequential and we run things again in sequential mode. Hopefully we can get some speed up. Okay. Now you see the time is going to be doubled. So for this reason, we cannot run multiple times, because if we run multiple times, we will lose our class time. But we will try to run at least one time and compare. If we could get speed up from the first time, then that's very nice. Okay, you see, we increased the time, the n to 200, which is 2 times bigger problem than the initial problem, but the execution time is not double, is more than double. Execution time now is more than double compared to the 100. Okay. So that's why here now the problem size increases. So here, when the problem size become bigger, so the opportunity to get speed up when you make it multi-threading is more high. Okay. Okay, we can see here it's 1 minute 19 seconds. Okay, so let us take this scenario. So that one is the first scenario. Then here we could say n equals to 100. Then after that, like that, here we can say n equals to 200, and then we put dash line. We calculate ts equals to 1.19.281. Okay. Close this. We go here, we control Z, then we convert it to parallel again, and we run with 200. Okay. Now we should see the improvement. Now we should start see the improvement, because the overhead here is almost the same. The overhead of initializing the 3 threads is the same. If the n is small or big, is still the same. The the initialization time needed to initial those 3 threads used to run the 3 functions is always the same, no matter how big or small is the n. Okay. So for that reason, here we could start see the improvement. So maybe you get like 30 seconds, or maybe 40 seconds, or maybe 1 minute. Depends. Sometimes the improvement, we cannot see the improvement until we use bigger number of n, maybe like 300 or 400 or 1000. We don't know. Okay. So that's why we take this example. We started with 100, then we move to 200, then we see how. If there is an improvement, then we may increase the number to 400, and we see how it works and how speed up we could increase, or we could get. Okay, now 1 minute 17 seconds, 0.662, right? So here TP is equal to 117 point. You see, now we started to get more speed up than the previous scenario. So let us now move to another scenario here, like that, and let us increase the number to 300. Okay, let us see how the execution time will increase. Okay, so we have to be patient a little bit, because this actually is an important task to decide whether to move the program to parallel or to keep it sequential. So we have to do kind of testing all the time when we deal with multi-threading. Okay, especially if the problem can be parallelized. If the problem can be parallelized like what we have now, but because the problem size is not that big, sometimes the complexity, we don't want to pay more cost for the parallelization initialization or overhead than the real execution time needed by the sequential program. Okay, I hope that's clear. Guys, during this time, because we still have to wait like 2-3 minutes, or even 5 minutes sometimes, we don't know. During this time, is there anything unclear? Guys, anyone has a question in this regard? Any part of the program is not clear?
I think no, Doctor.
Okay, that's very good. Do you feel like you understand how to convert things from serial to parallel?
After you explain it, I think I know already.
You see, now we increase the things to 300, but the time still 117.542, which is even less than the time needed for 200, right? Because this thing actually is not exactly measured. Why? Because the computer do a lot of other tasks, especially for my computer now, because I'm recording my desktop, so I run the OBS software, this one that records my my screen, records my voice, do some kind of what they call it, video editing, because I put my logo, UPM logo on the video. So there is a lot of rendering, video rendering is done on my machine now. That's why sometimes the CPUs of my computer are busy with other programs. So that's why sometimes you cannot see exactly what happened. You see? Now, this measurement for sequential for 300 is more faster than the time for sequential needed for to solve the n equal to 200, which is illogical. Okay, not logical. But anyway, we need to keep saving this because we don't have enough time to run multiple times. That's why we always need to run multiple times, like 10 times, 20 times, especially for the real life applications, because in the real life we have to make proper decisions and we want to measure things and we want to evaluate the performance. We better stop all programs on the machine that we want to use, and we try to run only the program that we want to test. We make sure that the Windows update is disabled, maybe antivirus update is also disabled. If there's background scanning for the antivirus, we also make sure that it's stopped because we don't want to make the PC busy. Okay, then we make our evaluation, performance evaluation, and after that we can run whatever we want. Okay, so now we run again for the second time. We need to measure the exact time needed for the sequential. Okay. Okay, now it's 118. 1.18.544. Okay, let us stop this and we return things back to parallel. Then we execute that. So now we test the parallel, okay, for the n equal to 300. Actually, printing on the screen is also making delay, extra delay compared to the sequential, because in sequential program we don't print anything, right? So that's why this one is I meant to make it actually, because this one is to reflect the extra overhead needed by the parallel programs. So I meant to make that to make extra overhead. So now what we need to do is to record the TP, or the execution time, for parallel mode, and we compare it to the sequential time to see whether we have a speed up or slow down. Multi-threading, guys, is very complicated. So even to this example that I give to you is very easy. So maybe you feel really confident. I don't want you to be overconfident, because now if you feel like you already have excellent background about multi-threading, I want to tell you that you don't have any good experience about that, because multiple threads has a lot complicated things more than you have learned in this course. Okay, it's not impossible to learn, but it's not as easy as this example. Okay, So don't take it very easy. If you are interested to build parallel programs, you have to read about it carefully. You have to take maybe some courses or maybe to read some books to improve your background, to understand the basics and the fundamentals, the concepts of the parallel. Okay, you see now is 2.32.928. Are you sure? So maybe I'm not sure whether we run that actually in no. So let us. I'm not sure whether that execution time here, the execution time that we run. Did we change the n to 300? I'm not sure really. So I need to make sure. I want to repeat now. Okay. Sorry. Okay. See. And here, Control Q, 300. We make sure that everything is correct. Then we run again. Oops. Okay. Normally, guys, as I said, normally, if the problem is very small, don't waste your time. Don't waste your time to convert it to parallel program. Okay? So we have, at first, as I explained during our classes, based on my slides, the first thing we have to consider before we start thinking about parallelizing things, even if the problem is parallelizable, we have to understand the nature, the size of the problem, the cost, the extra overhead that will be introduced by the parallel program, and we compare it to the cost of sequential execution. So if the cost of parallelization is more higher than the cost of sequential, then we better stick to the sequential program to avoid unnecessary overhead or extra execution time. Okay? I think here it's going to take more time than that. I think in the last time we calculate this two, I think the n still equal to 200. We wrongly, I think, evaluated the things. So the program name actually is what? I don't know what's the program name. Yes, this one. You see here if you show properties, I don't know, not properties. Go to details, feedback, resource. Okay, now time is 2:39. You see, guys, we did mistake last time. We did mistake. 2:39, 2.39.350. Okay, now as you can see, the parallel program improves the time from 2:39 to 2.32. So here, this is only for n equals to 300. But if we increase the n to 1000, for example, it could require like 20 minutes for the sequential program to finish. Then maybe for the parallel program, it could take like 5, 6, 7 minutes. Okay, so the speed up will increase whenever the problem size increases. Okay, is that clear, guys?
Yes, doctor.
Yeah, okay, that's good. So the improvement here, when we increase to 200, the improvement is only 2 seconds, right? Almost 1.5 or about 2 seconds. But here the improvement is about 7 seconds or maybe 6.5. Okay, so if we make it 1000, maybe the improvement will be about like 2-3 minutes or maybe 50% or 60% faster. Okay, so I don't want to convert this to 1000 because I tried that by myself. It takes very long time, very long than you expect. That's why I don't want to waste the time of our class, and we just need to move forward and to calculate the speed up. Okay, so now the first part of the assignment we already done, because here the requirements is run the program in sequential mode and record the duration time consumed to finish the task in sequential mode, T1 or TS. Okay, then second, find how the program could be transformed into a multi-threading program. We already have done that. We changed the call of the functions to different threads and we run them separately. Then modify the code to transform the program into multi-threading programs. We have done that. Run the program in parallel and record the duration time consumed to finish the task in parallel mode, which is TB. We already have done that. So the last thing, save your project and put the folder in zip file and upload it to here before the deadline. Some of you guys have not done the last part. So I remember one of you guys sent me the program in a text file. Anyway, I considered that, but next time in this course or even other courses, you have to carefully follow the steps. I said here, save your project, put it in a zip file, so you put it in a zip file. No need to make it PDF or make it text file. Why? Because I want to open your project and I want to make sure that it's run. It could run. Otherwise, if you send it to me as a text, sometimes I cannot realize the flows you make. So for that reason, I have to build my own program, my own solution. Then I copy your text, your code, I put it in there. You waste my time like that. You will waste my time. So if I have like 5-6 students doing this wrong things, then instead of I finish in 1 day, I will need to finish in 2 days or 3 days. Okay, guys? So please, next time, follow the steps. Follow the guidelines. Okay? We still have the final exam. So if you send me anything wrong in the final exam, I should cut some marks from you. Okay? Yeah, don't do that, guys. Okay? So important notes here, if you have a function as blah, 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 you can call it in different thread as this. So I already give you hints how to make things, to convert things from sequential to parallel. So that's why the task is very easy to be done. Then the second part of the assignment, which is assignment 2, here based on the recorded T1 and TB in assignment 1, calculate the following. So speed up where S is equals to TS over TP. So let us here calculate. Okay, let us consider, because this one speed up is very small. This one, there is no speed up, there is slowdown. So maybe later, if we still have time in the class, we go back to this case and we calculate the slowdown and we calculate the overhead and the efficiency, cost, optimality, and so on. Okay, let us start with the last scenario first. So S here is equal to, let me copy this better. We put it here. Then we only replace things. So equals to T1 actually is the TS here. TS. Some people will call it T1, some people call it TS. So here TS is 2.39. Okay, let us consider this to be half, okay, to be 5. So let us consider that 395. Okay, we round this value to 395. So this one will be 2.395, and this one will be rounded to 232. No, this one is 9, so it will be 1. So this one will be 330. Okay. Okay. To make the calculation easier, guys. Okay. So here, this one over 3.330. So it will be equals to, let us open the calculator here, and we take the numbers, 2.395 divided by 3, oh sorry, 2, this one, not 3, 2 divided by 2.330. So it gives us this number. So if we round the things, this one will become 9, this one will become 8, and 8 will become 3, right? So we make it 1.03. Okay, so the speed up is 1.03. Okay, so this 3 is means 103%. Right, 103%. So we had 3% speed up, right? So this is how to be calculated. And now for the efficiency, what we need to do is to take the 2.395 divided by, we open this, we see how many processors we use. Actually, if we calculate based on my machine has 8 cores, so we don't use them actually, because the problem here actually is uses only 4 cores, because we have the main thread and 3 subthreads for one for each function. So in total we have 4 threads. So we expect that we will consider that only we have 4 processors. We only have 4 processors. I don't want to consider that we have 8, and later we will see what will happen if we have extra processors or extra cores than we exactly need. Okay, so we calculate the execution time for parallel 2330. Then after that, it will give us this result equals, let us consider that here in this line. So okay, let us this function doesn't, this calculator doesn't have I think the braces. Let us try 395 divided, oops, I don't know what happened, 3.395 divided by, we use braces, no braces. Okay, what we need to do actually first, because this calculator is very limited, so what we need to do is to time 4 by 2.330, then we get the result. So here the thing will be 2395 divided by 9.32. Okay, so again we take this 2.395 divided by 9.32, and the result here is equals to 0.254. Okay, because 7 will be rounded, so this will become 4. 4 will stay as it is because it's less than 5. So the efficiency is only about 25.4%. Okay, it's 25.4%. Okay, here we have two ways to calculate the efficiency, right? So what if we take the sequential, the speed up that we get here, and we divide it by the number of processors. So the speed up we have in the previous step is 1.03 divided by 4 processors. It will give us what? It will give us exactly 25.4. Why? Because it's the same thing actually, which is 1.03 divided by 4. So, or maybe, okay, like that. So you see that the result, why? Because we rounded some values. That's why the result become a little bit different. But the difference is very small. Like 0.257. Okay, so the difference is very small between the two laws actually, or the two ways of calculating the efficiency. Okay, so no matter you use this way or that way, both of them are correct. Okay, so I delete this, then we go directly. Okay guys, before I move, so far everything is okay?
Yes, Tolu.
Yes, doctor.
Okay, good. So here for the cost optimality, what we need to do is to calculate the optimality or cost optimality C, which is equal to P times the TP. P is the number of processors, which is 4, times TP, which is 2.330, okay, which is equals to, like that, 4 times 2.330, which is 9 by 0.32. Okay, this is the cost optimality. Is that clear? Okay, the other thing, or the last step here, is to calculate the overhead O, which is equals to P times TP minus TS. So here, what we need to do is to calculate P times TP, which is exactly the value of C, because C here is equal to P times TP. So this means this equation could be changed to C minus TS. So TS, like that. It's the same thing, same equation, but in different form. Okay, so I will keep this also, or like that. So because here we also have multiple options. Okay. So this one, P times TP, is already 9.32, so we directly put the value 9.32 minus TS, which is 2.395, which is equal to what, guys, here? Minus 2.395, which is, you see, 6.925. So this is the overhead actually. This is what they call it, parallelization overhead. Okay, guys, is that clear?
Clear.
Yeah. Okay. So what if we take the same thing here, the same thing? This one actually we will consider here we will consider that P is equal to 4. Okay, what if we consider that B is equal to 8? What will happen here? So you see that the speed up is very little, the efficiency is more lesser than the other scenario, because here we have big number of processors. So if we see here, the speed up actually will not change. Speed up will not change, but here this thing actually will change. Why? Because this one actually is going to be changed to 8. So this one will be 8 times 2.330 means 18.64. Okay, 18.64. So if we finish this part here, 2.395 divided by 18.64, it will give us like how much? It's exactly the half of the last result. Why? Because we multiplied the number of processors by 2, so the thing will give us the same result as before, but divided by 2. So here we have 12, 8. Okay, so if we make it to percentage, it will become 12.8%. So if we take 12.8% times 2, so it will give 25.6, which is exactly the same as the previous result when the number of processors is 4. Okay, so here let us continue. So this one, the cost optimality, actually we have 8. So now the cost will increase, right? Because we added more processors, but we don't use them. Why? Because we, in our program, we only use 4 cores. We only need 4 cores. So to increase the number of processors actually is not a solution. That's why we will see that if we try to increase the number of processors for the same scenario here, we will see that the cost is going to be multiplied by about 2. Okay, so here 8 times 2.330 will be equal to 18, which is last time 9.32, now is 18.64, which is 2 times bigger than the previous cost. Okay, 18.64. Okay, what's about this? This also will be increased because this one is equal to the result of C. So it will be 18.64 minus 2.36. It will become like 14 or 16 something, right? So 18 minus 0.64 minus 2.395, it will give us 16 point something, 16.245. Okay, from here we have the same scenario, same size of problem, but with different architectures here, with different architectures. So if we have 4 processors, then the result will be, the speed up will be 103%. So it will give us extra 3% of improvement in both cases of P equals to 4 or P equals to 8 is the same thing. Why? Because our program is going to handle only or to deal only with 4 threads. Okay, so that's why the speed up will not increase or will not improve, but at the same time the efficiency will be changed. So this one is 25% efficient. Why? Because the program mostly utilizes all cores or most of the 4 cores. So the efficiency is about 25%. But here, because we have more number of resources unutilized, that's why the efficiency is 12.8. What does it mean? This means that we paid for the hardware more than we needed. That's why we did not utilize the money that we paid for. Okay, or the hardware that we paid for. We don't utilize it as high as we can. So this here, in this case, the number of processors equal to 4 is much better than the efficiency will be higher than the efficiency in the scenario of 8 processors. Okay. Also, cost optimality actually is the opposite way of actually to tell you about the efficiency actually, but from different angles. So here the cost is 9 times, maybe not 9 times, is 9.32, but the cost here is more because we paid for extra processors, but we still get the same. So this one from here, the higher number of the cost optimality is the worse. So what we need to do is to minimize the cost optimality, but at the same time, we need to increase the efficiency, right? Because the higher the efficiency is the better. The lower the cost is the better. What's about the overhead? The overhead also is needed to be minimized. So the lower the overhead is the better. Okay, let us see, compare this. Here in this scenario, we have the overhead here is 6.925, but the overhead here is 16.245, which is 2 times worse than the previous scenario. However, the number of processors is increased or doubled. So from here, we can conclude that not always increasing the number of processors will improve the situation. Okay, this is the take away idea that we need to conclude from here. Okay, is that clear, guys?
Yes, doctor.
Yes.
Do you have done this in your assignment carefully like that? Anyone has a problem with that? I think it's very easy, right? Anyone had a problem with that? When you keep silent, I will consider that nobody has a problem, guys. So that's why it's better to ask if you have any issue, because now we are in the end at the end of our semester, and we still have the final exam. Okay.
Okay, doctor.
Yeah. So far everything is good. No answer. What happened, guys?
I think our assignment has been submitted, so I think it's good to know
Okay.
that we can improve by your explanation.
Okay. Okay. Good. Okay. Let us consider the scenario of the slowdown. Now we will go to the slowdown scenario, and we will consider. I will remove this, and we will consider that the number of processors is only 4, and we will see how the TS actually is 23. 23.7. Let us make it 7. We round it to be 1, so 24. We make it 0.24 because we need to round it to second, right? Sorry, 2 minutes, because this one is seconds, and in here we have it in minutes, right? So we need to convert it to minutes. Oh, this one actually minute and second is about okay, anyway, let us consider it as second, because the clock system is based on 60. That's why we cannot make it 0.24, because 0.24 is about half an hour, but if we convert it to 0.24, it will be about quarter, so that will not give us correct result. Okay, so 2.4 let us make it 2.375 exactly as it is here. So 3, then here TP is 24.163. Okay, so here I'm not going to calculate this, so we directly get the result. So the equation is TS 23753 divided by 24163, which is, as you can see here, it even couldn't get to 100. Okay, 0.983. So here we can see that the thing in percent is going to be 98.3. So here, if we calculate the degradation, if we want to calculate the degradation or the slowdown, so here it would be something like 1 minus 0.983, which is going to be equal to 0.017. So if we convert it to percentage, it will become 1.7% of degradation. Okay, so this one is degradation. That one here is speed up. Okay, why? Because 1 minus 1.03, it will become minus 0.3, which is reduced. So as you can see, if negative means the time is reduced, means speeded up, right? But here the time is increased, it's positive, because 1 minus this speed up value, it will give us a positive number, so it means the time is already increased by 1.7%. Okay, what's about the efficiency? Efficiency here is about, let us take the TP. TP is 24.163. This one TS is 23.753. So here, if we calculate that, this one is the same here. So what we need to calculate is 4 times where we are, 4 times 24163. 4 by 24.163. Okay, the result actually is going to be like that. This one here, 96.652. So here, if we calculate it, 23.753 divided by 96.652, it will give us about 24.5. 24.5. Okay, 24.5. So from here, guys, from here, you can see if we get 25% while we have 4 processors, that means efficiency is about the quarter, right? The quarter means about a quarter of the payload for each processor. But here we have the efficiency 25.4, so means this one actually is the improvement, right? But here it's supposed to get the minimum, it's supposed to get 25, right? But because here there is a slowdown, we can see the result is less than 25. That's why it still have efficiency, but the efficiency is less than the minimum, which is in this case of 4 processors supposed to be 25, right? So in this case, it's worse than the minimum. That means there is a slowdown. Okay, from here we can conclude that. Okay, let us go to the this one 233, which is the TP. So here, this one is like that. So this one processor P times TP actually is exactly the same as this. So we get this result here. As you can see, the number is getting bigger and bigger. Why? Because the cost optimality is very bad here. Why? Because we said the cost optimality must be minimized. So as you can see here, the cost optimality is very bad. It's a very big number, right? It's very close to 100, which means very high cost. Very high cost. We paid for extra processors, but we still have execution time even worse than the execution time of sequential program, right? So that means we almost lost our money for nothing, right? We almost lost or wasted our money to get no improvement, guys. Okay, this here for the overhead actually is C minus TS, so C is this. Let us copy that value. We put it here, and we copy the TS value, and we put it here. So create this 96.652 minus 23.753, which is, you see, the overhead actually increases. Why? Because we introduced extra overhead and its size is bigger than the size of the real execution time. Okay, so what scenario now is the best? Definitely, it's not based on the number of processors. To increase the number of processors doesn't mean that you get better performance. So if the processors that you increase it are not utilized, then you will get very bad results. So the thing is to balance. We need always to do kind of balancing between the requirements or between the hardware and the requirements of the software. Okay, we must get the optimal hardware that costs us the minimum that we can pay for to get the best results. So the minimum cost for the best result. This is the best case. Okay, so in this, so I want to remove this to make it easier for you guys. So in these cases here, the best scenario when we have a bigger size of problem with number of processors equal to 4. So here we can see the improvement is 3. So if we increase the size to bigger size, the problem to bigger size, then we will see the improvement to be higher than 3%. Okay. So for this reason, guys, I am going to take the risk now to run the program for bigger size. Oops. So I'm going to make this 500 or maybe 600. 600. Then we run, and we have to wait for that. Yeah, we have to give it a try. We see how the result will look like when the problem size increases to 600. Okay, it may waste 5 or 6 minutes, but better we have that experience. So we'll make another slot here. So the size is 600. Time is like that. We did this. Oops, it looks like the still here. Okay, still here. I thought that the program is crashed.